We should have a regular day of geometry today. I don't have any distractions going on right now. Go back to what we were doing yesterday. So if you have your green book, get it out. If you don't, okay. If you have your green book, get it out. If you don't have it, it's okay. Just get a sheet of paper ready for some notes. We're going to go back and finish up the review that we started off yesterday. We only did 3 problems. And remember, I want to try and hit the evens. So we'll start with 4, 6, and this was 8, I believe. I'll go back and double check that. But we were reviewing chapter 9, dealing with area and perimeter and all the above. Polygons, different types of polygons, different formulas. We're learning different words, just reviewing basically. And so let's go to where we were at yesterday. I believe this was number 8. I need a pen here. Number 8 on page 640 in the green book. And we use this formula for the rhombus, 1/2 of D1 times D2, that D's are diagonals. And we had the links here, and we had that this basically is measured in, you don't have to draw this, but I'm just showing you what area means to this problem. If you were to go in here like this and count up all these little squares inside of this area, you would count 252 squares. That's what that means, okay? And you obviously would have little triangle pieces, like right here. You'd have a little triangular piece. You'd have to add to that triangular piece. 2 triangles make a square, and so it's a lot of trouble to count that. So I'm going to start a new page, and we're going to start with problem number 10 on page 640. All right, and so we're doing review for chapter 9. And this has been a long time coming here, I'm telling you. We've been doing chapter 9 for so long now, okay? So we've got 4/29 as the date today. Those of you who are turning in your work, keep doing that. That's great. Keep going. We're not sure, but I mean, I don't really know what to tell you about grades at this point, other than I don't know what I'm allowed to tell you, but at this point, I'm not really supposed to be talk much about grades. So just keep turning in stuff. For one, it benefits you to learn this material. For another, it shows me that you're participating, and I can have a dialogue with you and connect with you. For those of you who have done a really good job of turning your stuff in, keep it up. I know who you are, and it will all come back to help you in the long run. Just upload your stuff, and if you're having any troubles, if I'm noticing on there, which I haven't noticed, that anybody's had any trouble because you've just taken notes, basically, I can help you, with a specific problem. But right now, we're just basically just cookie cutter, working out. All right. Oh, look at this. The area of a kite. Look at this. I've got a kite right here. I've got 2 kites, actually. I'm going to show you all this. I'm going to see if you can see this. I don't know if I can have to turn this upside down. Look, I've got 2 kites. We were flying them yesterday, or 2 days ago, and they're all together. Look at this one. Does that look like a kite? I was flying this one yesterday. It flies pretty good. I don't think it's kite shaped, right? It's not really kite shaped. It's more, you see how it's got the little legs, it's got little streamers there. That's one kite. Well, we're going to learn about kites today. Look at this kite. Does that look like a kite? Nope. It looks like something else. It kind of has a kite shape to it. I guess you get a diagonal from where my hands are right there. And then if you turn it on its side, you can, they obviously cut away. They subtracted this little area right here from the kite, and it's kite shaped. Now the first one I don't think was very kite shaped, but let's get back to what we were talking about with the formula. right? Okay, so the area of a kite formula is a lot like the area of a rhombus formula. So it's still going to be 1/2 d1 d2 like that. And so we're going to have the area of a kite where d1 is 32 meters, which is very long, by the way, for a kite. A meter is like the length of the distance from the floor to a doorknob. If you were to, if you were to open a door, that's 1 meter, right? That's 1 meter. This is 32 meters. That's a pretty tall kite. All right, and your D2 is equal to 18 meters. So let's fill in the blanks here. We're going to take this and fill in the blanks now. So we're going to say A equals 1/2 of, let's pull this back. A equals 1/2 of 32 and 18. Well, half of 32 is 16. 16 times 18. Let's see. 16 times 18 is 288. So we have 288 meters squared. So the area of this kite is 288 meters squared. All right. So that's how you do number 10. Let's draw a line. Let's move on down. Now we're going to have a normal, pretty average geometry day today because there's nothing stopping me. Yesterday I had a lot of stuff going on. So, all right, let's read what this says. We're developing formulas. This is section 9.2. So what we just got through was section 9.1, developing triangles and quadrilaterals and all that stuff, all those formulas. Now we're dealing with circles. You see that? And here's our formulas for our circles. We'll get into that in more detail in just a little bit. And we're going to start with number 12. So we're going to look for the area of circle J in which the circumference is this. But we're going to need to know two things here. So the area of a circle is pi r squared. And the circumference of the circle is 2 pi r, right? All right, so let's go. So I'm writing area equals pi r squared, and the circumference is 2 pi r. So I wrote those two things down. The one thing they gave me is, well, I'm going to go ahead and do circle J like this. So there's the center of my circle, and I need to know what that radius is. So let's look at short number 12. We aren't given the radius, but we are given the circumference, which is 14 pi. You see that? So 14 pi, I can put in terms of circumference here. Now check this out. I can divide both sides because I've got a common factor here of 2 pi. I can divide both sides by 2 pi, and look what I get. Done. Look how fast that was. So you divide both sides by 2 pi here. Obviously, they go away here. Divide 14 by 2, you get 7. Divide pi by pi, that goes away. So your radius is 7. And so now I'm going to plug that 7 into this equation right here. So I'm going to put 7 right there. And I'm going to have 49 pi. So my answer is 49 pi yards squared. Okay. So this is radius is 7 yards there. Okay, so that's how you do number 12. Now this is chapter 9, and obviously it was a really long chapter, so this is going to be a pretty long review. So let's look at number 14. So we had to do two problems. This is more like what I would think, and if I were to pick a problem that would be pretty similar to something on the ACT, it would be more like this, because you have to know two different things just to figure stuff out, right? And you have to work backwards too. Boy, they love that stuff, right? So we got number 14. We got we're going to find each measurement, round to the nearest tenth. Now, in this case, round to the nearest tenth. You know, I'm just going to leave it in terms of pi. I'm not going to round to the nearest tenth. I mean, you could theoretically go in. Well, heck, let's do it. Okay, let's go round to the nearest tenth. So we got 49 pi, and what do I get? 153.9, because that would round to the tenth place there. 153.9 yards squared. So if you were to follow the directions just like it says, then you round to the tenth place there. So now let's look at number 14. But it says if necessary. All right, so the area of a regular pentagon with side length of 10 feet. So let's go over here and look at the information about a pentagon in the review. So it says the area to the nearest tenth of a regular hexagon with apothem 9 yards. Now the apothem is from the center of the polygon down to here. It's basically half of what I would call the altitude. Okay. So now we're going to do 30, 60, 90 rule. We have not really discussed that a lot. This is something that this is a geometric rule that we need to talk more about. We've gotten into right triangles and special right triangles, obviously. 3, 4, 5, 6, 8, 10, 5, 12, 13. Those are special right triangles, but we didn't really talk much about the angles involved here. So you have 45, 45, 90, 30, 60, 90. These are all special triangles. And then there's a theorem that goes along with the 30, 60, 90 triangle. So if one angle is 30, one angle is 60, and this angle here obviously is 90, then you're going to have a square root of 3 involved here by the rule, okay? And so x is going to be this distance from here to here, right? So it's going to be, now 9 square root of 3 is the distance from here to here. This is the hypotenuse. This is 9, obviously, right? And then according to the rule of a 30, 60, 90 degree triangle, so you have this angle right here, this length right here would be 9 square root of 3, and that's where that's coming from right there. Okay, and then you divide it by 3, which turns out this would be a third of that length, basically. And so I'll tell you what, let's go look at this. Well, now we're talking about pentagon, right? Our actual problem is considering a pentagon. This is a hexagon, so a pentagon would have a little bit different shape. And if we have to have this rule, I'll go pull that out of the book and show you. But we're just going to assume this is correct for the moment, and we'll prove it later. Okay, so the S, which is this length right here, see that? The side of the pentagon, the hexagon is twice the length of x. So that's why we have 2x here. So this length here would not be 3 square root of 3 like this part of this triangle. It would be twice that, so it'd be 6 square root of 3. So the perimeter is, a hexagon has 6 sides. So we have 6 sets of 6 square root of 3. And so that makes a perimeter of 36 square root of 3. The area is this formula, which we're going to need. It's 1/2 of the apothem times the perimeter. And we're going to need that in a minute to figure out for a pentagon. All right. So 1/2 of 9, the apothem, they said, was 9. And then the perimeter was 36 square root of 3. Working all that out, you get 280.6 square yards. What does this mean? If you were to put triangle or squares inside of this shape, you would count 280, almost 281 squares. Okay. Now a yard square is pretty big. It's 3 feet on each side. So, half the length of some people mainly, some people are 6 feet long. Up to your waist. That's how big a yard is. So, Anyway, so let's go look at what a pentagon is and let's draw it real quick. And we're going to see if we need that formula. All right, so let's go down here and draw a pentagon. 1, 2, 3, 4, 5, pentagon. And then here's going to be my apothem there, okay? And they want this length here. We'll talk about that. And then this right here is your right angle. So what kind of angle is this right here, okay? So in geometry, obviously, if you look at a circle, if you were to make this a circle, like in circumscribe this pentagon with a circle, what you would get is 360 degrees total all the way around. Like if this were the hand of a clock, you would go click, 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 360 degrees all the way around in a circle. So basically what they want to know is if I go from here to here, how many degrees is it? How many degrees is this hand click, click, clicked all the way to right here, straight up and down? All right, now let's discuss a few things here. So if you'll notice, if I go straight up and down here, this would be 180 degrees. So obviously we are less than 180 degrees. Are we less than 90 degrees? Okay, 90 degrees would be here. 90 degrees would be here. So we are less than 90 degrees. Are we, 30 degrees? Are we 40? Anyway, so what we're going to have to do is deal with a formula. So we're going to go look up the interior. I'm going to show you on. I'm doing this for a reason. I'll explain what I'm doing here in just a minute. This line right here is not necessary. So if you think of this kind of like a blades of a fan, like that. This is the exterior angles of a pentagon. I'm going to talk to you about that in just a second. I'm going to go Google the interior angle of a regular pentagon. Okay, so let's go to interior angle formula regular pentagon. Okay, and let's see images. And let's go dig into this real quick. Okay, so I don't know if I can pull this up. I'm trying to full screen this for you guys so you can see what's going on here. Here we go. Okay, so we've got an equilateral triangle, a square, a regular pentagon, a regular hexagon. And so you see how that says 120 degrees right there? That's important. So in other words, every angle here is 120 degrees. This angle right here, you can see this. Let me zoom in a little bit more. Maybe I have to brighten it up a little bit. Okay. I don't think you can see this. It says 108 degrees. Can you see that? 108 degrees on every single side. So instead of a hexagon, we've got a pentagon. Okay, and so if you had your apothem going from here to here, and then your another hexagon, hypotenuse going from here to here, you need to know this length. Well, this angle 108 is important for you to know, okay? So obviously we have a 90-degree angle here. If this were our apothem, it goes straight up to the middle. And then we go from here to here. So let's see what we can do about that triangle in the middle. Okay, this is more like what I'm looking for here. So we've got, this is a hexagon, right? And there's your apothem and your radius. I'm looking for one that is a pentagon. So we've got a, okay, so there's our, more like what we're looking for here. Here's our apothem here. this distance, this dotted line is the length we're looking for. We need to know how long this is, and we know that this angle right here is 108 degrees, okay? Now, if this is a regular pentagon, then this should be, well, let's keep going. Keep digging. All right, so there's exterior angles and interior angles like I was drawing a minute ago. It looks like the fan blade, so you have extensions coming out like that. All right. And now, let's look at this real quick. So if you'll see this external angle right there, this external angle, this internal angle is 108 degrees. We said that for the regular pentagon, right? The external angle would be the internal angle minus 180 degrees, because of this, you see this straight line here. This makes 180 degrees. So what's 180 minus 108? Well, it's going to be an acute angle. So 180 minus 108 is 72. So the exterior angle here would be 72 degrees, okay? So let's go over here and look at this. I'm just hitting a few high points here. And it doesn't really matter if we finish completely today, because I can take as long as I need. So you got the exterior angles are 72 degrees all around here. Now that's important. And so we need to talk about the sum of the interior angles in terms of an exterior angle, okay? And so now, trying to find a good formula for this, or a good picture that represents what I'm looking for here. It's more kind of like it right there. All right. Now we're going to type in a couple of words: apothem, regular, pentagon. Okay. Now we're going to hit a couple of things here. Okay. So it's finding, it says we're going to, remember the key to this is we were trying to find the area of a regular pentagon with side length. This is number 14. Let's draw a couple of things here. Let's go ahead and, number 14 has a side length of 10 feet. So that means from here, let's say from here to here is 10 feet, right? And then from here to here would be half of that. So that would be, okay, let me show you. I'm writing it, I'm not showing you, okay? So we've got, here, I'll clear this up. So we've got a regular pentagon, okay? We've got this apothem going here. We've got this other hypotenuse going here. This length from here to here is 10, according to the problem. And so all this is supposed to be regular, so it's not very pretty, right? Okay, so from here to here would be half of that. That would be 5. The key here is I need to find this angle right here, and we're just going through, taking it slow. This is 108 degrees here. I just want you to kind of see what's happening here. This is 72 degrees, because if you add 108 and this is in 72, excuse me, you got 180 degrees, excuse me. And so this exterior angle, I'm looking for that formula for the exterior angle and interior angles here. Let me see if I can pull up what I need to pull up here. Let's see, that's not what I wanted. I typed in apothem of regular pentagon. Okay, now there was this image here. Let's see if this helps you. This might work. Okay, so let's see if I can blow that up here. Okay, so obviously we have a pentagon, right? So now this isn't very clear because it's not clear on my phone. It's real fuzzy looking. I just wanted you to see what I'm looking at here, okay? So if you see how this is, okay, it's hard to read that. Let me zoom that back. So we've got 360 degrees, right? All the way around. If you were to break that into 5 separate sections, so like here, think of this like a hand on a clock. Click, 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 5 all the way around. You break this down into 72 degree distances. So from here to here, 72 degrees. From corner to corner. Well, we're not going from corner to corner here. We're going halfway. So according to this, halfway would be 36 degrees. So I'm gonna put a little arrow and put 36 degrees right there on that angle. Okay. So what does that mean? Let's blow this way up. Okay. So we've got a big old apothem here. That makes 90 degrees. And we've got this base of the Pentagon. And we've got this hypotenuse going here. This is 36 degrees. So we need to know how big, how many degrees this other guy is over here. So we're going to figure out, okay, how many degrees are in a right triangle? Well, this is not a special right triangle. It's not a 30, 60, 90, 45, 45, 90. There's no real neat, pretty rules for that. In this case, it's 36 degrees, 90 degrees, and then what else would we need? Well, so we would have to have 180 for the whole triangle. And I'm going to subtract off 36 and 90 to get the number of degrees for this angle right here. Okay. Now we're getting a little bit deep with this one. So let's see, we got 180 minus 36 equals minus 90 equals, and I get 54 degrees. Okay. So this angle right here would be 54 degrees. Now, okay, so let's look at what this apothem would be. Okay, obviously we know from here to here was 5, right? So we know this length is 5 because the total length from here to here was 10, right? So we're trying to find the area of the thing, and we can't really do this without knowing the formula. So there's your formula. And what does this A stand for? A stands for the apothem. What does this P stand for? Big capital P stands for the perimeter all the way around. Well, we can get the perimeter very easily. All we have to do is say 5 times 10, right? Because each side is 10. Now, all we have to do is find this apothem. We got to figure that out. I know what half of 50 is. That's 25. But what are we going to multiply 25 by? Okay. And so in this case right here, you know this is 5. Now, in geometry, you're supposed to know a couple of things already. That if this angle were the same as this angle, if these two angles were the same, then their opposite angles, their opposite sides would be equal. Now, I'm just going to, you can estimate this problem without having to know any kind of, without having to know any sort of math or trigonometry. And we're going to be dealing with trigonometry in just a second. This is kind of going to be your first little bit of trigonometry. And so I'm leading you up to it, okay? So if you'll notice that this angle is 36 degrees, so it's kind of small. This angle is in the middle, and this angle is really big. Well, if this angle is really big, that means this side is the biggest side, this opposite of that right angle there. That means this side over here, where it opens up to the opposite side here, the apothem, would be in between. In between what? It'd be in between 5 and something really large, okay? So it's a little bit bigger than 5, but it's probably not going to be, this side's not going to be 10. It probably won't be. Actually, I know it won't be. It's going to be in between 5 and 10. So you could estimate this to be 25 times, maybe 7.5 or something like that. Okay, now we're running out of time on this lesson. So I'm just going to wrap this up by kind of describing what's going on here. So let's focus on this 54-degree angle here. I'm just picking one at random. Now, what do I know? On this triangle, I know an adjacent side to that angle. So I'm going to call 5 as my adjacent. And the apothem would be the opposite. Okay, so that's important that you know that. So adjacent and opposite, we need to know a couple of things. You could do so, ka, toa. Oscar had a heap of apples. You could do it like that. And so if you'll notice, I have opposite and adjacent. Opposite and adjacent is going to be tangent. You see how it's got O and A there? So tangent is equal to opposite over adjacent. Okay, so you gotta remember, if you're using a calculator to calculate this stuff, you're going to have to make sure your calculator's in degrees. So my opposite side of the 54-degree angle, so if I were to find the tangent of 54 degrees, right? And my calculator needs to be in degrees, so I'm going to go make sure my mode is right. So if you'll notice right here, it says radian. I need to change it to degree. Okay, so now it's flashing degree. I just click mode and then that. So now I'm going to type in tangent of 54 degrees. So if you look at tangent of 54 degrees is bigger than 1. It's 1.7376, right? Well, we can write that in 1.376 as an estimation down here, okay? And now if you'll notice, your opposite side to your 54-degree angle is the apothem, so I'll put that as A. And then the adjacent side would be 5. So I'm going to put 5 right there. So really, we've got a formula that we can solve for the apothem, and that's what we're looking for here. So what we had to do is pull this trigonometry trick out of my hat in order to figure that out. So we're going to multiply both sides by 5, and let's see what the apothem is. Okay, so 1.376 times 5. I'm going to delete something here. I get 6.88. You remember how I told you it's going to be in between 5 and 10 because we knew it was somewhere in the middle? And I said, you might could do 7.5 or something like that. Well, it's actually 6.88, okay? Mathematically, it's 6.88. Would I have been absolutely way off? Not really. I wouldn't have been off much at all. I was just estimating. So what's half of 25 or half of 50? That's 25 times 6.88. And so my area of my shape is going to be, let's see. Now, tomorrow I'm going to dig a little bit more into, trigonometry because we have not discussed that. And that's kind of what I would have taught you anyway. And if we were in the classroom at this point, you would have already had some trigonometry by now, okay? Let's see, what was our units? Let's go back to our original problem. Our original problem was feet. The area of the regular pentagon with side length 10 feet. So the apothem is going to be 6.88 feet. The area is going to be feet squared. And so the final answer is, I'm going to write answer here. And I'm going to leave it. We may have to stop right here, and because I don't know if I'm running out of time or not. If it shuts off, it's okay. I'm not worried about it. We'll just start again. I'll probably do some tomorrow morning, just to kind of catch up. I missed a day last week, so I just want you to be able to catch up. Let's hit some high points real quick before we wrap it up. I might do another problem here in just a minute, but we just did the area of a kite, and there's the formula for the area of a kite, diagonals. So you just multiply the diagonals. Boy, that's easy, right? And then number 12, that was number 10. And then we did number 12 on the review, which we were given a circle. We didn't know the radius. They gave us the circumference, which we were able to find the radius off of that circumference, which was 7 yards. And then we substituted 7 yards into the area formula for a circle, which is pi r squared. And so we wound up with 49 pi. We could have left it in terms of pi, which is fine, but the book said to round it to tenths, and so we did that. And then down here, we kind of messed around and played around with Google to try to learn what a apothem was, what a regular pentagon looked like, the interior and exterior angles of a pentagon. So our interior angles are 108. We said from here to here was 72 degrees, because if you took 360 degrees and divided it by 5, you get 72. So you have literally 5 separate sections of 72 all the way around. And then we said, okay, this is half of that, so this angle is going to be half of 72. We got 36 degrees here, and then 36, 54, 90. Okay, now we could have chosen 36 as our angle to base off this SOHCAHTOA stuff here, sine, cosine, and tangent, but we didn't. We chose 54, and 54's opposite side was the apothem, and the adjacent side was the 5 here, this length of 5. And so we had apothem over 5, basically, is what we would get here for our formula. So the tangent of 54, which is in degrees, is 1.376. And that equals this ratio. Basically, what this means is sine, cosine, and tangent, all they are is ratios. They're opposite over hypotenuse, adjacent over hypotenuse. And roofers use this all the time. People who are in construction use this stuff all the time. Of course, they have a book that has this stuff already calculated out in it, because when you're up on a roof and you're in the danger zone, you don't need to be pulling out a calculator. You need to be worried about you not slipping off the roof. Okay, so they pull out a book that has these numbers on there, so they won't have to think about anything other than their safety. But these numbers are calculated from this stuff like tangent 54 degrees, okay? And tangent of 54 degrees is 1.376. We divide both sides by 5, or multiply by 5 here, and we got 6.88. We estimated it to be between 5 and 10 because it should have been somewhere in the middle, the smallest side and the longest side. This is somewhere in the middle. Now you could go and find the longest side really quickly, the hypotenuse here, just by using Pythagorean theorem. And you could go in and say a squared plus b squared is c squared. So we could say the small side plus the medium side equals the large side, all squared. And I'm going to wrap up today figuring out what that hypotenuse is, and then we'll stop the notes right there after I've calculated this out. So I'm calculating out 5 squared plus 6.88 squared equals, and then I square root that answer, and I get 8.54. So I knew it's going to be less than 10. So C is equal to 8.54. What was it, feet? Okay, so this is 5, this is 8.54, and this is, what would we say, 6.88? Is that what we said? So now we know all the information we needed to know in order to figure out a regular pentagon. Now, could I have cleaned this up? Yes, but I really want you to understand the parts that we can segment off are right here. So we could segment off this. We could segment off this. Okay. And then this section here, and then this section here. These are all different segments of things that I've talked about since we began this problem. Okay, so take your time, write a few things down, and then we'll start with number 16 tomorrow. Now let's see how many